Hey everybody. So today I'm recording this video. We'll see when you guys get around to actually looking at it. But there is an assignment that's due on Monday that is just a quick introduction of a new notation, probably a new notation for most of you, that is going to give us this change from a sequence of numbers to a series of numbers. And so quick before we get into that, what that means is a sequence is just a list of numbers. This, comma, this, comma, this, 5, 10, 15, 20, whatever. A series of numbers is not just 5, 10, 15, 20, but it's 5 plus 10 plus 15 plus 20. And one of the things we're going to be looking at is how to add up a long series of numbers. And so today's topic, whatever today is, whether it's Thursday, Friday, Saturday, Sunday, or early Monday morning, is a new language, a new way of representing a summation, and that's going to be something called sigma notation, which I will switch over to presentation mode to show you what that looks like. All right, here we go. This is sigma. Class, this is sigma. Sigma, this is my second hour honors functions and trig class. Sigma is this symbol. This is a Greek letter. So just a quick look at the Greek alphabet. Just like our alphabet is the ABCs, the Greek alphabet is the alpha, beta, gammas. In fact, the first two letters are alpha and beta. Alphabet, that word actually comes from those two first letters of the Greek alphabet. One that we're looking at today is the uppercase sigma, and you are familiar with actually quite a few of the letters that show up. You certainly know what the number pi is. Well, it comes from the letter pi, the lowercase pi from the Greek alphabet. You're probably familiar with delta from a science class. We describe change by using deltas. Well, and if you've ever seen any sorority or fraternity house, they're usually named using Greek letters like, I don't know, gamma, delta, epsilon, or something like that. But anyway, that's what this letter is. It just is the uppercase letter S from the Greek alphabet, sigma. Now, what it tells us is that we're doing a sum. So when you see the sigma, we're doing sigma notation. And this is telling us that we're adding up a whole bunch of stuff. Sigma means sum. It means we're adding a whole bunch of things up. Now, this is a specific notation, and right now this is a little bit of a foreign language. So I'm just going to start by introducing and showing you what these things mean. I've got an n squared over here. I've got an 8 up on the top. I've got n equals 4. What is that supposed to mean? What this is telling us is, starting on the bottom, when I say that I've got sigma notation, I read the n equals 4 first. This tells us our starting value of n. We're starting at n equals 4, and we're going to keep counting and adding terms up until we get to the maximum value of n that shows up here on the top. So we're going to start at 4, we're going to go to 8, and in sigma notation, we increase it by 1. There's no skipping 5, 10, 2, whatever. We're going to start at 4 and go up to 8. So we're going to have n equals 4, then 5, then 6, then 7, then 8, and then we stop. And what we're doing with those numbers, 4, 5, 6, 7, and 8, is we're plugging them into the term expression. That's what we see showing up over here. And this just tells you what n is doing. So I read this as the sum of n squared as n goes from 4 to 8. Again, I'll repeat that. When I see this notation, I think I'm doing the sum of n squared as n goes from 4 to 8. And then actually doing it, the first chunk of your homework is expressing or expanding an expression like this. We're starting at n equals 4. So n squared, when n equals 4, we start with 4 squared is 16. And then I plug in 5. 5 squared is 25. And then we keep going until we get up to n equals 8. Let's see, I've done 4 and 5. Next comes 6. 6 squared plus 7 squared plus 8 squared. And then we stop. Now, because I'm at the edge of my screen, because we've gotten to the largest value of n. And then we add them up. And I am pulling out my calculator. You can't see my video right now. At least I don't think you can. And so I'm adding up 16 plus 25 plus 36 plus 49 plus 64. I'm getting a total of 190. So this sum of n squared as n goes from 4 to 8 is 190. And that's a big part of the first, well, it is the first part of your homework assignment, is just taking something like this, writing it in expanded form, and then finding the sum. So for something like this, I read this as the sum of 2n plus 3, as n goes from 2 to 6. I'll start plugging in 2. Let's see, 2 times 2, 4 plus 3 is 7. So we've got 7. Plus, let's see, plug in 3. 3 times 2 is 6, plus 3 is 9. 2, 3, 4 comes next. 4 times 2 is 8, plus 3 is 11. Then I plug in 5. 5 times 2 is 10, plus 3 is 13. And for a lot of these, you're going to start noticing patterns. Here we see that they're going up 2 each time. We probably could have guessed that from this formula because it's 2n. Every time n increases by 1, we're going up by 2. You could kind of think of this almost as a slope of these terms. It's not really, but we can think of it that way. So I know the next term is probably going to be 15. Check and make sure. When I plug in 6, 12 plus 3 is 15. And then we add up these terms. Again, I'll just pull up my calculator and do 7 plus 9 plus 11 plus 13 plus 15. I get 55 when I do that. So the sum of these terms is 55. Then we get to something like this. Find the sum as n goes from 1 to 600 of 2n plus 3. Now, I don't think you've got any of these in your homework this weekend, but I do want to show you this one because this is going to lead us into some of the formulas that we'll see next week. I think next week. We'll have to see. We don't have too many days next week, but we'll see how far we get. If I were to start listing some of these terms, start with n equals 1. The first term is 1 times 2 plus 3, which is 5. N equals 2. We've got 2 times 2 plus 3 is 7. We saw last time that it's not a coincidence that the pattern is that these terms are increasing by 2. So n equals 1, n equals 2, 3, 4. 4 times 2 plus 3 is 11. I'm going to put some dots. I'm going to put ellipses here saying I don't want to write out all of these terms because, well, there's 600 terms here. I'm still being asked to find the sum. So I'm going to show you a sneaky little trick for us to find the sum of a set of numbers like this. When we get to the end of this, the very last term is going to be 600 times 2 plus 3. So that's 1203. And I left some space here because I want to see some of the other terms. The term that comes before 1,203, either by plugging 599 into this expression or just remembering that these terms are going up by 2. So the second to last term will be 1,201. And the third to last term will be, let's see, 1,199. I don't want to plug all of these into my calculator. That's literally 600 numbers that I'm plugging into my calculator. That would take me a really long time, but I'm going to be able to do this anyway. Here's how. I'm going to take that 5 plus 1,203. There's a reason I'm doing this. When I do that, I get 1,208. And when I do 7 plus 1,201, well, that's 1,208 again. And then 9 plus 1,199 gives us another 1,208. When I have an arithmetic series, we'll be talking specifically about arithmetic series on Monday. Actually, we might do both arithmetic and geometric. But anyway, when I have a series that's increasing by a constant amount like this one is, the pattern is going to hold. The sum of the first and the last is going to show up many, 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 many times. I should put ellipses there. We're adding a whole bunch of numbers, but then I can say that this is equal to 1,208, and as long as I can figure out how many times that shows up, I'll be good to go. It's 1,208 how many times? Now it's tempting to say 600 because I've got 600 terms here going from 1 to 600, and I'd be counting all of them twice. I've got 1,208 between these two terms, between these two terms, between these two terms. And so I actually have 300. I've got half of the total number of terms tells me the number of times I've got 1,208. So I can actually plug this into my calculator. I've already done that, so I'll just cheat. Well, that's not the right answer. I must have changed this problem. I'm just going to plug in my calculator, 1,208 times 300. I do remember I changed that from a 2 to a 1 because I wanted an even number of terms. And I get 362,400. Wow, cool. If I have you do 600 terms, there must be a shortcut. There must be a way that I want you to do a problem like this one. We'll talk more about that next week. Today's more about just recognizing, representing things in Sigma notation and translating from Sigma notation. So the last couple of problems I have here are similar to the last couple problems in your homework assignment. By the way, it is a fairly short assignment, not because you're asking for it, but because that's just the way this one goes. Here's my sigma. I'm adding up a whole bunch of terms. Let's see, I've got 1, 2, 3, 4, 5, 6. So I suppose I could go from n equals 1 to 6. But I don't know if I want to commit to that. I'm going to think about what these terms look like. Let's see. Going up by 3 each time. This is an arithmetic series. The difference between the terms is a constant. So maybe I could do... Well, how about this? I've seen a lot of people give this as a wrong answer. I've seen a lot of people do something like this. They'll say, well, let's start at 28. And I'll go up to 43. And I want to repeat, this is wrong. This doesn't work. I want to show you why this doesn't work. But I've seen people do this. And let's do n plus 3, because they're going up 3s. So I'll start at 28. I'll go up until 43, and they're going up 3s. This is wrong. I want to be very clear. This is wrong. What this would give me would be, well, when I plug in 28, 28 plus 3, this would give me 31. And the next term would be 29. 29 plus 3 just gives me 32. 31 plus 32 plus 33 plus until I plug in 43. The last term I get would be 43 plus 3 would be 46. This is definitely not what I'm trying to represent here. So one way for me to fix this, I'm just going to get rid of those because that does not work. That was incorrect. One way that I could do this would be to be a little bit more sneaky about this and say, well, I noticed in the previous problem, and I guess the problem before that, this 2 times n is what made the terms go up by 2s. So if I want these to go up by 3s, let's go with 3n plus something. Now, if I want to start at n equals 1, that's usually a pretty good place to start. I just need to make sure that whatever I add on here is going to give me 28. So right now I've got 3 times 1 plus something. Well, if I want to add 3 to something, 28, it must be 25. Plug in 1, 3 times 1 plus 25 is 28. Plug in 2, 3 times 2 plus 25 is 31. Plug in 3, I get 34. Plug in 4, I get 37. Since I have 1, 2, 3, 4, 5, 6 terms, if I go from n equals 1 to 6, that works pretty well. This is correct, but it's not the easiest way to do it, and in fact, it's not the way that I'm going to suggest that you do this problem. But again, it's not wrong. So I'm actually going to take this, I'm going to keep this to refer to in just a moment, but I'm going to put it off to the side for just a minute and say, let's take a look at a different way of doing this problem. It's using something that we learned earlier in this chapter. I'm still going to go from n equals 1 to 6. I want 6 terms. I want to start at 1. 1 is a nice number to start at. Since these terms are increasing by a constant amount, I know how to represent a sequence of numbers that are increasing by a constant amount. This is an arithmetic sequence. It just happens to have plus signs in between, which makes it an arithmetic series. But I know how to get the nth term of an arithmetic sequence. Just the first term plus the common difference times n minus 1. There's the formula from last week. Actually, I guess that's from 2 weeks ago. From the quiz last week, but from the lessons from a couple of weeks ago. And let's make sure that this actually works. When I plug in 1, 1 minus 1 is 0. 0 times 3 is 0. 28 plus 0 is 28. When I plug in 2, 2 minus 1 is 1. 1 times 3 is 3. 28 plus 3 gives me 31. And when I plug in 6 at the end, 6 minus 1 is 5. 3 times 5 is 15. And guess what? 28 plus 15 gives me that 43. So remembering the nth term of our arithmetic sequence lets us get to the answer a little bit more easily without thinking as much. It's just recalling this formula. Again, this is okay too. This will give me the same thing. In fact, if you distribute that 3 and simplify this, you'll end up getting the same expression over here. All right? So if you have a sequence, or a series, I should say, where the terms are increasing by a constant amount, this is going to be pretty easy. I'm going to ask you to pause. Try to do this one on your own first. And now I'll do it and make sure that you got the same thing that I got. Let's see. I've got, 1, 2, 3, 4, question mark. How many terms are here? Now I'm going to have to do a little bit of work here. I'm going to say that the nth term of this sequence of numbers that are being added together is the first term plus the common difference. We're increasing by 6 times n minus 1. And I want to find out what number term is 97. You had to do that on your quiz last week also. Or if you're looking at this on Thursday, you did this on your quiz today. Or if you're looking at it on Friday, it's the quiz you did yesterday. Anyway, here we go. So 97 is what number term in this sequence? We'll just do a little bit of algebra here. I'm going to add 5 to both sides and get 102 equals 6 times n minus 1. Divide both sides by 6. Plug in my calculator in case you couldn't hear the clicking sound. 102 divided by 6 is 17. So if 17 is n minus 1, that means n is 18. Sweet. So now if there are 18 terms, my sigma notation is going to be n goes from 1 to 18. And I've got my expression already. Each term is going to be negative 5 plus 6 times n minus 1. And there we go. It's expressed in sigma notation. I even like it in this form because I can recognize the formula for an arithmetic sequence within the series formula. And then finally, the last one I'll do today, because it's the last type of question, is if you've got a geometric series, it's going to work the same way. I've got sum, and goes from something to something, and I recognize this as geometric. Each term is twice as big as the term that came before it. So I'm going to write down my formula for the nth term of a geometric sequence and use that in my series. First term times the multiplier to the n minus 1 power. And if I use this as my formula using the terms of the sequence to plug into the series, I can start with n equals 1. 1 minus 1 is 0. 2 to the 0 is 1. 3 times 1 gives us our first term. And I can just count the terms. 1, 2, 3, 4, 5, 6 terms. So I've got n equals 1 to 6. And just to make sure this works, 6 minus 1 plugged into the formula. 6 minus 1 is 5. 2 to the 5th is 32. And 3 times 32 gives me 96. So here we go. This geometric series written in sigma notation. And that's it. That's all I've got for this one. Hopefully the assignment goes pretty well. Most of the assignment is just the stuff that came earlier on. Just recognizing, understanding how this formula works. What does sigma notation mean? So you should be just fine with that. But if you are not, if you've got questions, certainly shoot me an email. Get in touch with me. But we will be moving on to the next section on Monday. Make sure you work on the assignment this weekend. And I'll see y'all on